Okay, so for the last session of the day, we're going to have Kyungjoo Kim, who's going to do the hands-on demo with some MATLAB code demonstration. So yeah, you'll be able to get your laptops out and use them. Yeah, thanks.
Hi, I'm Kyungjoo Kim, and I'm going to give you kind of interactive lab session about coupling the local and non-local problem that Mauro already explained in the previous class. It's a very simple code, so you can easily follow and the things. So first thing is you need either Octave or the MATLAB with the optimization toolbox. And this optimization toolbox is you need to purchase the license. So if you can use the Octave, it's probably easy for you. So, and also you can download this code from this GitHub repository. And in the command line, you can just type git clone and this address and on the CM4. So first, let's make sure that you get the code in your laptop. Everybody get the code now? Or any technical problem? So it's easy. I mean, you don't need the MPI and then you don't have to compile the code. So you just download and then run the script and you will see this coupling problem. Oh, wake up. Okay, so we are just going to solve the 1D Poisson problem. And Mauro shows the kind of a big 3D problem, but I cannot really ask you to compile trillions, and it's going to take about at least 1 day to compile the code, and you do some kind of iteration, and it's not really easy to work on the 3D code. So we give this the 1D code. So in the 1D code, we solve this simple Poisson problem, and we have the force function is given from the manufactured solution, and boundary condition also is given from there. So probably you already know about basic of the finite element method. In the finite element method, we use the piecewise linear function, and in the weak form, we get this one. As Mauro already explained, this kind of interaction is only between the two nodes. So you get this tri-diagonal matrix, and then you solve this problem and you get the solution. And on the other hand, if you solve the non-local problem, the weak form is described in this way. And you also notice this is kind of a double integration. So it means you have another loop inside of your integration routine. So it's computationally more expensive. The main problem is about this bandwidth is large, and this is simple 1D problem, and you can expect how large your matrix size is growing in the 3D problem. So in the first example, you can see
anybody was able to get the code? Because I took it full and in I state. It should be.
Yeah,
You
I mean,
didn't change
okay.
the repository, right?
I didn't change. I mean, did you
I don't know
get
why
the
it's-
code?
I got.
Yeah.
So you just download it.
Yeah.
So yes,
Yeah. Okay. You download it. Okay.
as I go to the website and download it.
Okay.
And that's the quickest.
Yeah. Okay.
Yeah, so
Just making sure that it.
so you can just clone like this. Oh, really? But it's okay. I already have code. So this code is based on the Marta's the research code, and if you want to reproduce the all the results in the Marta's the paper, you can use the code located in this directory Marta, and then I do some modification on this here, so you can play with the code. So first example is about I want you feel the complexity of this non-local problem. So you run the two problem and it will show the things. So there is help routine and run local problem, and you're going to see that this the input and output parameter. So run the local problem, and n is the number of element. Let's say 10. And this epsilon is used for some manufactured solution, but here it's a dummy argument, so you don't really need. And test is the number of problem. So its test is the problem ID. For test 0, it's going to show this is the matrix pattern, and you're going to solve some kind of a solution with discontinuity jump. And this is approximated by the continuous Galerkin. So you can increase, and then you get another matrix is generated, and then you get the refined solution. So this is the local problem. If you want to do non-local problem, you just add this. And here, because I put this epsilon is the interaction range. And now interaction range is the smaller than mesh size, it gives some warning. So I can increase this, and then it's gonna complete the integration. And as you see, this non-local problem takes a lot more time than the previous one. And this is the solution. And then we are solving this equation using the discontinuous Galerkin method, and I plot the value here. So, I mean, if you have any questions, you just interrupt, because it's more interactive things, not the demonstration I show and you take it, and it's not like that. So this is the test number 0. And the other one is like you can test with the different manufactured solution. And here, different manufactured solution is described on this exact solution.m. And you're going to see this the solution. In the test 0 case, I use this exact solution for giving the boundary condition because it does not have the exact solution. But the rest of others is giving this, it's gonna reproduce these solutions. So you can play with.
So
yeah.
is it because you are using Octave, so such way your matrix is like that? So MATLAB is like
The other way?
yeah, it's the other
Probably yes.
way. Like that.
Oh yeah.
Right.
Yes.
Yeah. So I would just
So yeah, so this is just warming up about the, and also this kind of
oh yeah. Yeah, it's like flipped. So it's flipped. Just
Yeah.
so the index is a bit different. So his one line is on the
Yeah.
bottom, my one line is on the top.
So it goes this way.
Yeah.
yeah.
I mean, I guess MATLAB tries to make it more as you write it. The
So
labels
it's,
and not.
yeah, and
Yeah.
that's more.
It's more user friendly.
Yes.
So as you see, if you increase the interaction range, it's gonna make the even bigger matrix, and it will take some forever. So this is kind of a motivation why we want to couple the solution between this non-local and local approximation, because for some discontinuity or some to detect the irregular behavior of the solution, we want to use some nice formulation that is found easily detected from the non-local operator. But it's expensive, and more often it takes a lot of memory, and simply you cannot solve the problem. So, and this one is just the second problem of and it just reproduced the simple Poisson equation. Any questions so far? And this is the MATLAB code. You can easily figure out how the code is working.
I don't know why, but like if you set the epsilon is 0.01, I got warning here in our local neighborhood is smaller than the mesh size.
Because if your the non-local operator is meaningful, your non-local operator, this epsilon neighborhood size is supposed to be bigger than your mesh size.
Yes, yeah. So if it is smaller than the mesh size, it will take the mesh size automatically, right?
No.
No.
You give the epsilon is smaller than mesh size, it just work like a local operator.
I see.
Because it cannot gather the information from the other side.
I see. Okay.
So in theory, if you reduce this epsilon smaller and smaller, and then your non-local operator behave like a local operator.
I see. I see.
So this is the manufactured solution. If you choose the test 1, you're gonna reproduce the linear solution, and for the quadratic solution, you choose test 2, and test 3 is the cubic, and this quadratic form is the test 4. And this is the test 0, and this is the representation of the source function that created this discontinuity. So now as I said, you can kind of test how this epsilon affects the operator. And this one is kind of I run this script, and then you're gonna compare the local and non-local operator. The way that I compare this one is like I'm giving this source integral case. This source the representation is given from the manufactured solution, and here test 5 case, I just give the third order the force function, and it's gonna produce the solution, and that error the difference is depends on this the epsilon and then this fourth order derivatives. So if you run this the comparison, and whenever you need some kind of argument information, you can ask help here. And here, let's say 10, and interaction range is the 0.12 and 4. And it's going to solve the problem. And in the next iteration, the epsilon is become half. And you're going to see these two solutions is getting converge each other like this. So the representation of the operator is different, but its kind of numerical meaning is the same. So everybody can run the script and also follow what this exercise is doing. It's very simple, right?
Wait, so is red the non-local? Is red the non-local?
Yeah, red is the non-local and then black is the local. So in this way, because this operator looks similar, when you control this epsilon, you can actually blend the two operators by controlling the interaction range. That's kind of another approach to couple the two problems. So is it okay to move to next slide? Okay. So now we are going to do the exercise on solving this problem using the two different discretization methods. So for the simplicity, we divide this domain into the non-local region and then local region. In the non-local region, it includes something we call the horizon area. And also this is the overlap zone. Overlap zone has to also include this epsilon amount here. And Mauro already gave the lecture about how the alternative Schwarz method. They just moved their data each other and then exchange the boundary information and solve independently until these two boundary conditions match each other. So here you can always help learn coupling, and you can use this alternate. And the first parameter is the how, and also you can change the domain here. So here I describe the problem domain is the 0 to 1.75, and non-local domain is going to be 0 to 1, and the local domain is the 0.75 to 1.75. And then we give the number of elements, and let's say about the 12 element here, and for the local element we can give the little bit less number. It doesn't have to be matched exactly. It just gather the information each other and use the interpolated value to running this alternative Schwarz method. And epsilon is supposed to be bigger than the mesh size. And then let's say test problem 3. Oh, not help. And And then problem is set up, and it runs the iteration, and it stopped when the difference is small enough. So this is the final solution, and this is the initial solution. So these two methods doesn't really match each other, but after Schubert's iteration, you get the matched solution. Because this is the 1D problem, there is no kind of surprise. We just match the two values and solve two problems independently until they agree each other. But in the 3D, it's kind of matching these two displacements in the same. It's kind of a very tough condition. So sometimes you cannot match the problem. And here also, if you run the test problem 0, this is the kind of our work scenario. Like the discontinuity is described by the non-local operator, and smooth solution is the given from the local operator. And this is the initial configuration, and then this is final configuration. And this is this vertical bar represents the local domain. Here we solve the local, and then this one is the non-local domain. This one is the epsilon. So you can change the domain over here, and then you can see how it affects the coupling method.
So something I didn't mention is that this non-local operator, in particular the non-local Poisson, allows solution to be discontinuous. So like the normal Poisson equation, you know that you have it's a diffusion operator, so your solution is very smooth. But the non-local operator can have these discontinuities, and it's really a feature of this operator. And that's also the reason why this can be used to model things like the test fractures or discontinuity, because that's allowed by the model itself.
And the other one is we are using the same problem, and actually it takes quite amount of time because we do not provide the adjoint operator, so it computes the gradient based on this finite different method internally. And here we use the optimizer given from this octave. So for example, we use this MATLAB function. This is the function minimizer, and the UNC means this minimization function is the unconstrained. So using MATLAB, it's kind of easy. Just call this MATLAB function, and you get this coupling solution. But as you see, it's gonna take quite amount of time. And here, they kind of showed they show the same solution, because this is still smooth, and then we use a kind of manufactured solution. But in reality, what we really want to solve is kind of two different physics model. Like Mauro already presented, the one is kind of DF theory, and the other one is the PMP. And they do not really agree each other, because the one has the oscillation, and the other one is kind of a mean value theorem. And in this case, how do we couple these two problems? And the optimization-based solution is kind of give the means to control the coupling mechanism. You can control like what's the meaningful coupling of the two physics, and what variable have to be minimized. So the first, you can play with this, and in the next, this one is just an example. And this one is another example that I just made. And I just give some kind of oscillating force. And then the fourth term is the diminishing with increasing the position of x. So at the end, it behaves like kind of a homogeneous source term. And here is I solved this problem using the Schubert's method, and the other one is the optimization-based one. in the Shubart's case, it just connects. It finds out the value from here, and then you just extrapolate to the satisfy the boundary condition at the end. So it means if you kind of control the overlap zone, like going back and forth, that it's gonna pick up this point, and if you increase this overlap zone like here, it's gonna pick up the point here. But when you solve the optimization based the coupling, you don't really pick up the value from here. It just minimizes this misspeed. And it actually the kind of nice way that you actually couple the two different model in kind of a consistent way. So here learning the same thing, and then you can pick up this test problem 6. So it pick up this point here. And if you use if you change the domain, so now they overlap between the 0.7 and then 1. Run the same problem. So now it pick up this point. So you see the difference? The solution kind of depend on the oscillation. I mean, in this level, we already assume solution is kind of this oscillation is attenuated, largely attenuated already. So we can approximate this one is kind of a single line. So that's kind of our basic assumption. But when you solve the real problem, you don't know how this attenuation goes. But if you solve, now it takes some time, but if you solve with the optimization based one, same problem, it always try to minimize the misspeed of these two models. So meanwhile, just if I show this source representation of the number 7, it's like this. I give the sine function and divide by the position. So if the position is large and this source term is going to be 0, in the local problem, I simply assume this source is 0. So now, yeah, it's kind of aligned in the middle. So this kind of optimization based one, yeah, it's expensive, and this is 1D problem. But it's kind of a minimizer, and we are solving the convex problem, so it always converges. And also, in the kind of a high dimensional problem, it gives some kind of reasonable solution.
So it looks like if you crank up epsilon enough, then I'm not sure if it's not converging or if it's just, well, it says solver sub prematurely for me, and you get some funky solutions.
Can you show us here?
Well, so the one I did was run coupling optimize. I used the same parameters as you had, but with epsilon equals 0.35.
Mm-hmm.
And I used the case 4.
Case 4 and then 0.35.
Yeah. So this one sort of, it seems like that's sort of right on the edge where if epsilon is much bigger than this, then the solution gets even stranger. Is that, I don't know, if epsilon gets large, do you expect to have problems, or is this?
Let's see first. I mean I tested many problems, but kind of yeah. if you find kind of some case that this code does not work, I mean, it could be bug, but it may dictate something.
I am in MATLAB and not talked to it, but I don't know if that'll.
So can do this will work also with the full non-local, without the guide.
Yeah, see, it works when it has more or fewer points.
It's an art.
So it depends on the age of reps. If your reps are over age, that ratio will go up.
Because this yeah.
Yeah.
Oh,
But my
Really?
yeah. Mine sounds picking up across a lot.
It says converge.
yes, we just find out something is wrong, and
Can you look at the gradient?
gradient.
Or
So this is the expected solution here. 0.2, 0.35, 0.1. Do you have enough number of points already? Control point we minimize. Is this really minimization? It has the overlap range.
So can I see your parameter again? Because I know you can do something else.
Yeah. I would do.
Oh yeah, so I guess just because the exam is too large,
I think I'm not 100% sure about this, whether this is the really solution or not, because this optimizer is the stop at the gradient is almost 0. So it says this is the minimum that kind of minimized this misfit.
Oh, yeah.
I think it's I will optimize this packages not really working.
yeah, that might be.
It also.
So the gradient is 1. Is it I mean, as epsilon increases, the model becomes more and more different, non-local and non-local. So I don't know actually.
Oh, I sent it to you.
But they are
Yeah, I like
So
to
the
try
alternative
to
works okay, right?
Yeah.
Yeah, okay, so the alternative works.
Plus, I tend to lose things.
See?
So the alternative so works okay, just the optimization doesn't work.
Yeah, if I use the
So
alternative.
Schwarz, okay. So it's a transition. So yeah.
It was different.
Yeah, this is good.
Epsilon was smaller.
Yeah, so
And
So-
bigger.
But what's successful? What's the
But see, this is
It's
the
a
exact
error
same
message,
See, that's
or-
not horrible.
Can you see
Successful?
equal to the 7? What does it mean?
So it has to do with optimization.
I think this is the optimizer problem.
Yeah.
So,
Because the API is too small and your mesh
Gradient must be provided.
trust the region.
yeah, yeah, this is the one problem when you use just kind of external library to call this, and then you don't know what's going on inside.
Yeah. I mean, plus we are not giving the join, so it's like a derivative free method. I mean,
Is it still?
So, a lot of iterations.
Okay. So you can kind of keep playing with this parameter, and somehow someone already report that the optimizer does not really work correctly for the large epsilon, and that's something I cannot really handle right now because I don't know what this optimizer actually do internally. So this is what I prepared for the hands-on session, and I hope you actually do something with this code, and then to get the better understanding on the Schwarz and also optimization, the coupling, and also the local and non-local operators. So.
You're finished?